with Susanna is there, and I was looking for error, but also error. So yeah. If you have any questions, just interrupt me. There are lots of small details that we need to know, like basics of this, so we can get something. Right. So what we care about. So either we set a graph from GN1/2 or from distribution where we, for example, a graph from GN1/2, then plan say a poly-sized clique, some k vertices that we choose, right? And we want to distinguish these two distributions. And we want to do this in polynomial time, and we don't really know how to do this. And the question is whether, we can do this. Okay. So what do we know? We know that there is a quasi-polynomial time algorithm where we just check all, say, 3 times log n size cliques, and we check whether any of them is a clique, and if one large enough clique, we can actually distinguish. But we don't know any better. And also, if k is very large, say like square root size, then we can, by spectral method, somehow detect that there is a large clique plot. And otherwise, we kind of believe that this is hard. This is the plant-to-clique conjecture, and I think like one goal of this line of work is to prove the plant-to-clique conjecture for bounded computational models. Okay. All right. And these bounded computational models are proof systems, or like the algorithms for proof systems. So let us do proof systems, and let me tell you what is known. Okay. So suppose I give you the claim that if I sample a graph in format random, like GN1/2, where I include every edge probably 1/2 independently, and I claim that there's actually a clique of polynomial size. Okay. So for refuting this claim, what do we know? Well, we know basically that for tree-like resolution and Null-Stellensatz with no dual variables, there we have this optimal entity log size bounds, okay, on such reputations. And otherwise, for these natural proof systems, we know nothing. Okay. Now we can introduce these weird proof systems. We can play with the definition of the proof system, and then we know a little bit more. Namely, for regular resolution, is resolution where on every prediction to axiom path resolve every variable at most once. There we can actually plant the clique of some constant times log n size, and we still obtain this optimal n to the log n. And again, this is it. For this particular problem, we don't really know anything else. Now there are some results of similar flavor, which would also like to mention. So by Rossmann, we have beautiful monotone and abstract lower bound for clique. And for resolution, we have some non-height lower bounds. You can play with encoding instead of playing with the proof system. You can read the encoding and then proof lower bounds. There we know actually something for resolution and something slightly stronger than resolution. And then there is this beautiful line of works of degree lower bounds for SOS, but unfortunately no size lower bounds. Right? Then we will move these into the log n size lower bounds for Unary Sherali-Adams. Far so good? So our results, so we proved that Sherali-Adams with polynomially bounded coefficients almost surely require size n to the log n to refute the claim that the graph, sampled uniformly at random, contains a poly-sized clique, a clique of size n to the 1. Okay. And this, at least qualitatively, establishes the plant-to-clique conjecture for Sherali-Adams. All right. Yes.
Does it extend to our framework when the size of the clique is a constant key, you get n to the...
Yes. Okay, good. I'll have a formal statement later.
Good.
Yes. So I just want to discuss GN1/2 here.
Yeah.
We'll extend to
Okay.
But not beyond G, not beyond logarithmic size.
It's your formal statement.
Okay. Good. All right. So I'll introduce the Sherali-Adams proof system, then the clique formula, restate the results, and then we'll dive. All right. So Sherali-Adams, we're given variables x1 through xn, x bar 1 through xn, and a polynomial system where I assume that the polynomial system contains the Boolean axioms as well as the negation axioms, making sure that the power variables are the actual negation of. then a Sherali-Adams refutation is simply the sum of axioms multiplied by some polynomials plus non-negative linear combinations of monomials over these variables. And these should, as a form of polynomial, sum to minus. Right? I say the Sherali-Adams is F bounded if all these CAV coefficients are bounded by F, and all coefficients appearing in these QI polynomials are bounded in magnitude, also by F. Then the size is number of monomials occurring on the left-hand side of such a replication. You can expand everything out without cancellation. And the coefficient size is the sum of the magnitudes of all coefficients. Standard, I hope. Then we have the formula. Yes.
There's some reason you bounded the lengths of coefficients, but those are absolute values. Sorry.
Absolute values. Yeah, no, not the length. You're not vectors.
Sorry.
Yeah.
Wrong setting.
All good. Okay.
Sorry.
All right. So how do we encode the Clique formula? Well, I want to look at k-parti graphs G, and I want to encode the claim that there is no clique in this k-parti graph with one vertex per block. Okay, so how do we do this? We have k sets of vertices, V1 through Vk, each of size n. Yeah, I'll draw the edges, like there are edges between all the partitions. I'll only draw the ones that are adjacent to each other because I'm a bad artist. And then there are Boolean variables per vertex, non-Bauer and Bauer variables, which are the negation of each other. The intended meaning is that such a variable is one if and only if it's the k-clique. We have Boolean axioms, making sure everything is Boolean with the negation axioms. And then the more interesting axioms, we have the block axiom, ensuring that we pick exactly one vertex per block. That we sum over all vertices in each block. We say that we pick exactly one. And we have the edge axioms, making sure that we don't pick any two vertices that are not adjacent. So for every edge that is not present in the graph, introduce an edge axioms, ensuring that at least one of the two vertices is not the same. Okay. Now I hope it's clear that this formula is satisfiable, even only if we have the clique with one vertex per block. Right? Everyone happy so far? Good. Very good. All right, then I need to tell you our distribution. So we are over here for k-parti graph, partitions of size n, and we include every edge independently with probability p if it's in distinct parts. So then our formal statement is that if you sample such a graph with probability p at most 1/2, and we know by capital B the maximum clique size of the graph, then with high probability, Sherali-Adams requires coefficient size n to the omega of d to refute the Clique formula, the claim that the graph contains a coincidence. Yes.
Seeker, you have here a concentration, but still is the maximum, the clique size of the formula you are working with, or is it the threshold for the given field? What is D?
D is the
Is it for a random variable or not?
No. I want it's a threshold. Capital E, the threshold. Yeah, okay, fine, okay. Yes. So yeah, if it's not the threshold, then this doesn't apply, and we're always at the threshold. So yes.
What does it mean? Requires coefficient size.
So coefficient size is the sum of the magnitude of all coefficients.
The sum of the magnitude. Okay. I mean, there is just no proof or no short proof with such coefficients.
There is no proof.
No proof at all.
Yes.
Oh, no proof.
There's no proof, or there's a proof of this coefficient.
So what about the trivial?
Sorry. All proofs require this coefficient size.
There is at least one coefficient that has the size regardless of.
Sorry again.
Oh, there's at least one coefficient that has this size regardless of the length of the proof.
No. The sum of the coefficients.
This is the sum of
I think we're
the sum of the
coefficient
magnitudes.
size, we don't understand that it's the sum of the
Yes.
coefficient sizes.
Yes.
The word
So
sum
the
is-
coefficient
Yeah,
size
good.
is the sum of the magnitudes.
Either or
not
not
a
of
single
terms
one,
or.
it's just the sum of all.
Magnitude is absolute value or bit size?
It's absolute value.
Absolute.
It's the magnitude. I think magnitude is absolute. Yes.
Is there a difference?
So in particular, because the trivial proof is brute forcing,
Yes.
it will have exactly this, this sum of magnitudes because you have one in there for every, right?
Yes, exactly. Yes, exactly. So the trivial proof is to just sum for every tuple, like we sum all of those, we have. There you actually have n to the k many, right?
But you can do it on the deep
But
blocks.
yeah, you can only do d blocks and then you get n to the k. Because you know that yeah, you'll never see a clique size module.
Okay. So even the trivial proof is like blockwise, your proof.
Over d blocks. Yes. Yes. Okay. I'm sorry about the confusion. I really didn't see this. Okay. Anything else? Or? So and then as a corollary, like what I promised before, is that we actually get Sherali-Adams size lower bounds if we assume that our coefficients are bounded by some polynomial. And here the polynomial that's this C is independent of capital B. Like you first choose your proof system C, and then like for large enough D this. All right. Today we'll focus on the case P equal to 1/2. So hence B is roughly 2 log n. If you want to go to like the less than setting, the sparser setting, it's like, yeah, it's basically the same proof. It just requires some adaptations. All right. Okay, so let's move on to proof ideas unless there are questions.
What is the relative power of Sherali-Adams with unary coefficient?
So it's incomparable to resolution.
Sorry?
It's incomparable to resolution. Yes.
You cannot even simulate.
Cannot simulate resolution. So if you want to simulate resolution, you need really large coefficients. Yes.
So the proof in regular resolution for the k-1 partite graph,
Yes.
complete graph, can be done with quadratic coefficient size here.
I believe yes. Should yes. Yeah, I think we checked it. Yeah, yes. All right. So our main strategy is that we just write a linear program to search for minimum coefficient size Sherali-Adams refutation of P. It's not difficult to write down. You can write a linear program. And then just by duality, we will actually lower bound the minimum coefficient size. Okay. And so this dual object, I'll explain to you now what this is. So we want to obtain a delta pseudo measure, where you should think of delta as really small for this polynomial system P. And it should satisfy 3 things. First, it should be normalized. So it should map 1 to 1. It is almost non-negative. Okay. So for any monomial n, we want that the measure associated with this monomial is essentially non-negative, except like maybe minus this teeny tiny small delta. And then it should be small on axioms, even on weakenings of axioms. So any axiom multiplied by any monomial should be associated with a small measure in magnitude. Okay. Notice here that we do not require like any restriction on degree. All right. So this should hold for all polynomials, like all monomials. Okay, so this is how we'll lower bound the magnitude, the coefficient size of a Sherali-Adams. Let me just like convince you that this will actually give us a lower bound of the coefficient size. So if we have a Sherali-Adams refutation, we can apply mu to both sides, right? And then here, this first sum, we can expand the qi as a sum of monomials with coefficient c sub n, right? Now we know that by the third property, this expression here is lower bounded by the magnitude of c sub n times delta. Okay. Then the second sum each one of these expressions is low bounded by magnitude of C sub dB times delta. The right-hand side will be equal to -1, the first property. And so if we divide everything by 1 over delta, we see that indeed all these magnitudes sum with these. Yes.
Are you gonna bound the degree?
No. Okay. No, it's for any refutation of anything. All right. So this is the overall strategy. And now what remains is to come up with such a delta pseudomeasure. Right. So let me just state what we want to do. So our goal is to construct this n to the minus log n pseudomeasure for the Clique formula, where we sample G probably at random or according to this random model. And we should think of K as some small polynomial. Okay. And just to remind you, we want to find a linear operator mu, which is essentially non-negative, small on axiom, and maps 1. All right. So how should we think of such a pseudomeasure? I want to think of this pseudomeasure mu as a progress measure of monomials. Okay, right? It's small on axioms and it's large on 1. So I want to somehow think of the measure associated with a monomial as the contribution of this monomial towards contradiction. So one natural attempt is to somehow just say, okay, fine, but each monomial like somehow rules out a space or some set of assignments. And I just want to associate like the fraction of the space that a monomial rules out with each monomial. Okay. So I just want mu of m to be the fraction of assignments that the monomial rules out. In fact, I don't want to like consider all assignments, but only relevant assignments. So the fraction of relevant assignments that. So to make this a bit more formal, I need to define two things. I first need to tell you what are relevant assignments, and then what it means for a monomial to rule out. All right. So I'll draw the vertices of our graphs here, like in this K partition, right? Partition of size n. And I want to say that an assignment is relevant to us if there is a graph, so that this assignment is actually a solution to the Clique formula for this specific graph. Okay. So how do these assignments look like? Well, these are the assignments that pick exactly one vertex per block, right? And set those to 1. So this assignment identifies a tuple. It is a set of vertices with one vertex per block, and sets exactly the variables associated with these vertices in that tuple to 1 and all others to 0. And these are somehow interesting assignments to look at, because like if you have a graph that actually has a clique on this tuple, on these purple vertices, then this is actually like a solution. So you can think of these as potential solutions to our. Right. So just another one, these tuples, the relevant assignment associated with them. And then I have to tell you what it means for a monomial to rule out an assignment. All right. So let us look at this monomial xu times xv. I want to say that a monomial rules out an assignment, or actually a tuple, relevant assignment, if the assignment sets this monomial to 1. So what do I mean by this? Well, we said that these relevant assignments identify one vertex per block and set associated variable to 1, right? So if you want to have the monomial xu times xv to evaluate to 1, this means that you need to pick u and v into the tuple, so that the associated assignment will evaluate this monomial. So this is one such tuple that is ruled out by this monomial. This is another, and in general, it's any tuple that lives in this shaded region, in this rectangle.
Sorry, tuple. Vertices from the graph. That's tuple 3.
And the tuple is a set of vertices with one vertex per block.
So then what does it mean?
And what I mean by this is like any tuple that lives in this purple space. So it picks one vertex per block in the shaded region. So in particular, this lives in this purple region. And we can think of this as a rectangle because it has this nice product structure. And like if you look at all the tuples.
Not the relevant assignments.
So the relevant assignments are the assignments that correspond to tuples. So they identify one vertex per block and set the corresponding variable to 1 and everything else to 0. Okay, and then these are somehow the relevant assignments because there are graphs so that this is actually a solution to the clique formula, right? Namely the graphs that have a clique on this tuple.
It's not under your distribution, right?
No, ignoring my distribution, yes.
Still ignore, we still ignore the actual graph, right?
Yes, we ignore the actual graph, there is nothing to the graph. So.
Is it a homogeneous monomial? The homogeneous, is it the maximum?
I don't understand, sorry.
What's the degree of the monomial? It's precisely.
Is this precisely K? No.
So this is for any degree monomial I can define this, right? So we, in particular, we can look at this monomial.
No, there can be a block with all zeros.
No. My tuples identify one vertex per block.
So once you fix the blocks, there's only 1 degree.
But the monomial doesn't have to include all of the columns in that.
I think there is a confusion between monomials and tuples. So a tuple is a relevant assignment. A monomial can be extended to a tuple. But I think a tuple is k vertices. Monomial can be a sub-tuple, and then you'll count how many it can be extended to.
Yes.
Monomial is a rectangle. That's the right way to think about it.
So now you are
It's just a
defining
rectangle,
for negative,
cylinder, whatever it was.
Yeah, monomial is a rectangle.
Yes.
And it can have also intermediate cardinalities because it will multiply, so.
So when you say M rules out, you are not meaning that you are changing the blocks. It's just assignment.
It's just assignments.
Okay.
So we have this set of relevant assignments. And I want to say that a monomial rules out a subset of these relevant assignments.
Okay.
These are assignments illustrated. So let me try to do another example. So let us look at a monomial that actually has negations in there. Okay, so here we have the monomial not xu, not xv, xw. Here like a tuple, what does it have to do to actually set this monomial to 1? Well, it should not select u and not select v. It has to select w, right? And then anything on all other points. So these are the tuples. This is one tuple that is ruled out by this monomial. This is another one. And in general, it's again this rectangle that I shaded here, like all tuples that we live in this shaded. All right, very good. And just for sanity check, 1 rules out everything, right? Because it always evaluates 1. So that somehow it's the right thing. All right, good. So let me just reorder my slide. So I moved the idea up. Now, so now with these notions at hand, we can do a first attempt. So let us just associate with a monomial m, simply associate the fraction of relevant assignments that it rules out. Eventually take any assignments, that seems like a natural. Okay. So what are the good things that this measure satisfies? It only maps 1 to 1 because I normalized correctly. It's non-negative. If you look, if you look at the block axiom, which sums over all vertices in one block, then I'm claiming that and says that you have to pick exactly one vertex, and I'm claiming that this is 0. The measure of this block axiom is equal to 0. So why is this so? Well, the measure of each variable here, like somehow just picks like a fraction of the space. It nicely partitions the whole space of all tuples. So this is really like equal to 1, and it's just 0. All right. But this doesn't work because of the edge axioms. Okay, because the edge axioms, they rule out a huge fraction of all tuples. Right. So basically a 1 over n squared fraction of the tuples are ruled out by each edge axiom. So this doesn't work. All right. So what did we do wrong? Well, maybe we were a bit too generous with associating a monomial n with all relevant assignment intervals. Maybe we should be a bit more restrictive, right?
Sorry, can you say again what the problem is with the last line?
So the problem here is that the measure.
Too big or too small?
It's way too big. So we want that our measure on axioms, it's of size like n to the minus log n. It should be tiny on axioms. But here the edge axioms, we have measured at 1 over n squared. And this is way too big. So the best we can hope for is an n squared lower bound, which is not very interesting. So maybe we're too generous with all the assignments that we associated with the monomial. Maybe we counted some tuples that are just not relevant. They're stupid tuples that are easy to apply. So maybe like as a second idea, maybe we want to associate a monomial with a subset of all the tuples that it. And maybe an attempt would be to just say, well, let us just count all the cliques in the corresponding rectangle that we rule out. So let us just say our measure mu is now simply we sum over all tuples in the associated rectangle. And we just count the number of cliques in there that we rule out. If we rule out the clique, we do a lot of progress, right? That seems to be a good thing.
Cliques of arbitrary size of four fixed sides.
Case clique.
There are no, okay.
Yeah. Yeah. This will fail horribly. But just let bear with me for a minute.
Both for the show.
Yeah. So at least in expectation, when if we sample every edge with probability 1/2, everything is satisfied. Okay. I chose the normalization so that really the expected value of the measure of 1 is equal to 1. And it's not so hard to see that all other axioms are equal to 0. Like if you have an edge axiom, then clearly an edge is missing, so we don't have any cliques, so it's equal to 0. And the block axioms, just because we have this nice linear structure, it's equal to 0. Okay. This is a great measure, except that there are no k-cliques in our graph, right? So it maps everything to 0. All right. So we would like to recover from this somehow. And yeah, so let us think. So what is the problem? So the problem is that the expectation of the measure of 1 is actually 1, but this random variable is crazy, right? It's basically always 0, except once in a while it's huge. It's like roughly 2 to the k choose 2, right? Like if you have a single clique. So we want to somehow make this random variable better behaved. Okay. And then hopefully, if it's better behaved, then it actually concentrates around the expected value, and we can hopefully still maintain that everything else is small. All right. Okay. And this is the idea of pseudo-calibration from this celebrated SOS learner. Okay. So what is the idea? We first choose, like in our case, a measure mu that satisfies everything in expectation. We write out our measure mu in the Fourier basis, and we just truncate this sum of Fourier characters in a smart way. Hopefully, by doing this, we reduce the variance. By reducing the variance, everything concentrates around the expected value, and we're done. That's the rest of our plan. Okay. So we want to write it out in the Fourier basis. We somehow truncate the sum over these Fourier characters, and hopefully everything concentrates then around the expected value, and we're good. We can go home.
Well, you are still trying to pseudo-calibrate identically 0 function, right?
Yeah. But by truncation, it will. By truncation, it will become more interesting.
No problem.
Yeah. All right. So, okay. I have to tell you a bit about Fourier characters. Don't worry, nothing scary is happening. I'm also scared, or I am scared about Fourier analysis. It's gonna be fine. So we have a character for every edge where u and v are distinct blocks. It's simply +1 if the edge is present, -1 if the edge is not present. And for a set E, we simply let the chi sub E denote the product over all edges in this set. Okay? And in particular, like the empty character is equal to constant 1. All right. Now this was our measure from before, right? I want to rewrite this in the Fourier basis. And let us just look at a fixed tuple T. Okay, let us ignore the sum over the tuples. Now claim that this is just equal to the sum over all characters living on this tuple. Okay, so what are these characters that we sum over? We sum over edge sets that live on this tuple. Yes.
So usually with characters, we think of -1 as a Boolean variable being 1, and you have it the other way
Yes.
around. Is there the intuition for this?
For independent set, it's the right way around. For
Ah, I
it's
see,
the
you're
wrong way
doing,
around.
okay, so you're doing
Okay.
independent set based.
Yeah, like
Okay, yeah.
we'll see later. I really want it this way, but
Yeah, okay.
okay. So but yeah, so we're just summing over all characters that live on this tuple, like on this T choose two. I hope this is not too confusing. Now, if all the edges are actually present, then each of these characters evaluates to 1, right? So clearly, like if all the edges are present, then this is really equal to 2 to the K choose 2 because we have K tuples. Okay. And otherwise, if an edge is present, then we can cancel along this edge, right? We can look at every set that does not include this edge and sum it with the set that actually includes this edge. The one character that includes this edge will be the negative of the other, and they will cancel nicely. So this is indeed the indicator. All right. So let me clean this up. So we now said that the measure of u is equal to this thing, right? Now I want to introduce a bit of non-standard notation, and if you zoomed out because you know Fourier analysis, you should pay attention a bit now. So I want to identify edge sets that look the same as the same edge set. What I mean by this is, well, look at this graph H and the tuple T, and now I want to map this graph H onto the tuple T. Okay. If you look at the graph H and the mapping of H onto the tuple T, denoted by H of T, this is really the same edge, the same graph, right? Except that it can be mapped to different tuples. I can map it to this tuple, or I can map it to this tuple. It's still the same graph. So I somehow want to identify all these graphs as the same graph. Okay. So how do we do this? So what I want to say is that now we sum over all graphs in K choose 2. Okay. Like you can think of these graphs as really living above the blocks, like this green graph. And then we map this graph H onto the tuple T, like the purple one here. And then we sum over these characters. Yes.
So, I mean, yeah, so you're basically saying, yeah, looking at, yeah, the point is it's got H, yeah, sorry. You're on the small number of vertices. So you're just looking at the induced graph on one vertex per column, essentially. What does that induced graph look like?
Yeah, you can, yes, but yes.
Maybe another way of saying it is like you're just symmetrizing over the columns, right? Like there's a natural symmetry on the on each column because I can act on it by just permuting any column independently. And I'm just going to declare that my measure is invariant under this symmetry.
Very good. Yes.
Yeah.
Thank you. All right. And the main benefit of writing it like this is that I can swap the two sums.
Right.
Okay. And this is what I want. Like, because now I can like fix my graph H and then say something about winners. Okay. Just all right. Let's go back to pseudo-calibration. So what did we want to do? That we had our measure mu0 that with our fancy notation we can write like this. And now we wanted to like somehow truncate it to reduce the variance. All right. So is it even possible to truncate this sum in any way so that 1 is actually mapped to 1? Can we do this like at all? Is it at all possible? I mean, the very stupid answer is yes, it is possible. If I only allow the empty character, then we simply sum the size of these rectangles associated with the monomial, which is basically attempt 1. Okay, and what failed in attempt 1? In attempt 1, we had the problem that the measure associated with an edge axiom was too large. So there seems to be some tension there. So on one hand, we want to associate 1 with 1, but at the same time, we'd also like to say that the edge axioms are small. Okay, And if we just truncate it really aggressively and we only allow the empty characters, then we get into trouble for the edge axioms. And somehow we want to find like some middle ground where both of them both these two axioms are like well behaved. Get a question? Or it's good. Okay. And to just give you some intuition how you can truncate mu while maintaining that one is mapped to one, I'll do like a simple second moment calculation. Yeah, the second moment of the measure mu. Okay, and we'll hopefully see that, or we can convince ourselves that if we truncate by like not as aggressive as I suggested, by only allowing the graph H as empty character, we still get some concentration around. Right. So yeah, so for this, let us look at the second moment. And if we can show that the second moment is essentially one, then by Chebyshev, we get that with high probability, everything concentrates. Okay, fine. So I just wrote out our second moment. I'll draw a picture to the right side. So we sum over graphs H and H prime, over tuples T and T prime, and we now map H to T and H prime to T prime. Okay. And all you need to keep in mind is that the expectation of a single character is equal to 0, while the expectation of the squared of a character is equal to 1. So what does this mean for us? This means that this inner expectation is equal to 0 whenever an edge appears once, right? Because we have independence over the edges, so we can like put the expectation into the product. So this means that even if these graphs map to the same tuple, if the graphs differ, then there will be an edge that appears only once, and therefore the inner expectation is equal to 0. So we can really forget about the fact that we have two, that we sum over two graphs, we can just sum over a single graph. So the more like we're summing over different tuples T and T prime, but if these tuples actually differ on blocks where H has an edge incident to, then we again have a single edge, right? So these tuples really need to agree on all the blocks that our graph H touches. Okay. So really what we're left with is simply counting the number of tuples that agree on the projection on the blocks that H touches, and can be anything outside. Right. So we can rewrite our second moment like this. Then we can do some counting. Not so important what's happening here. Like we just have for every vertex that is touched, we have n choices, just because the block is of size n. And outside we have n squared choices because we're free there. Yep. All right. And then you can use the normalization factor. Let me just clean up. We rewrite it. Then we can rewrite it as the sum over I, right? Number of vertices touched by graph H, then n to the minus I. Now we can simply count the number of graphs H, so to create H graphs that exist. Let me just overcount very simply. We choose how blocks that are actually touched times 2 to the I choose 2, right? Just number of such graphs that exist, or graph upper bound. Now let me rewrite this as this exponential function, or a sum of these exponential functions. And so what do we see here? So we have exponentially minus I times log n minus log k minus log I. So we think of k as a small polynomial in n. So this log k is really some epsilon log n factor. So we see that as long as I is much smaller than log n, then this sum is tiny, right? It's really, really small. So this sum really, it's nothing as long as we don't sum for too large i's. Once we start to sum for large i's, we get crazy variance. So this somehow tells us that if we only sum graphs H such that they touch few blocks, like at most some small constant times log n many blocks, then we really map 1 to approximately 1. Okay? All right. So we have some flexibility in how we choose the truncation. Okay. So let me just summarize where we are standing. So we saw that if we truncate this mu0, we can somehow guarantee that 1 is mapped to 1. There's some tension between ensuring that 1 is mapped to 1 versus the edge axioms, that those are small. Now, with any further explanation, I'll just tell you how we truncate. Okay. So this is the actual definition of our pseudo measure. Our pseudo measure of a monomial M is simply we sum over all graphs H that have small vertex cover. So they have vertex cover at most D, where we think of D as some small constant times log n. And then we sum over all tuples in the associated rectangle and all the corresponding Fourier characters. Okay. Same calculation as on the previous slide that we just did, but a bit more involved counting, shows that 1 is essentially associated with 1. And so what it remains is to argue that mu is small on edge axioms and that it is basically non-negative. Now, what I wanted to do is I wanted to tell you a bit more about the edge axioms, and the other part gets a mess, and I'll not talk about this. Right? So is there anything unclear about the plan of what we're doing? All right. So in the last 5 to 10 minutes, I'll tell you a bit about the edge axioms.
Sorry,
Yes.
so far, when did you use that the graph doesn't have a Clique type of property?
I mean, I didn't use any. Yeah. Yeah. So far, I just used that we sampled it with each edge with probability 1/2 in the net.
Well, I guess for the lower bound, you don't really need to use the fact that there's no K-clique, right? I mean, if that's it. If it's sample a graph with a K-clique, the lower bound should work.
But yeah, the random properties that we actually need of the graph get quite messy, and they're not so easy to explain. But I don't want to say anything about this. All right. Any other questions? All right. So edge axioms. So where are we standing? So an edge axiom is simply the monomial x v1 times x v2, where the edge v1 v2 is missing. Okay. And if you look at the monomial multiplied by these edge axioms, this will identify some rectangle, which will be like smaller than the entire rectangle. We write Q as this rectangle and want to show that the measure on this thing is. Okay. All right. Now, let me just reiterate what I said before, is that if we have the character of some set E that does not contain this edge that is missing, that we condition on not being there, then we can sum over the edge set E plus set E with this edge, and this cancels nicely. All right, so we want to use this to simplify the measure on the measure of this monomial. Okay. So how do we do this? We can split the sum into 2 parts. So once we sum over graphs H, they contain this edge 1, 2. Once they do not contain this edge 1, 2. Okay, and because every tuple in this rectangle actually contains the vertex v1 as well as the vertex v2, then like when we map it, like we map to this missing edge, and we can cancel along this edge. So in fact, we can essentially cancel the whole sum except the ones where if you add in this edge 1, 2 into H, then we get a vertex cover that is above threshold. Okay, so these are the graphs that we like. All right, let me clean up this. It's the same as before. So now, a naive attempt to bound this would be to say, okay, fine, we just look at the innermost sums. These innermost sums, we have H fixed, and we sum over all tuples in this rectangle. And I'm claiming you that it's not so hard to show an upper bound that holds for any graph H and any rectangle Q. So what this is saying that the magnitude of the sum over all such tuples in a fixed graph, right, is bounded by n to the k minus vertex cover of H over 8. Okay. You can I would like to point out that this red part is the non-trivial part. If you just get an n to the k upper bound, this is trivial because this is just an upper bound number of tuples. Okay, so this vertex cover of H over 8 is the non-trivial. And then this bound is somewhat tight. up to the constants in the exponent. So we can plug this in, right? We can now just simply plug this in, but this will fail horribly because there are too many such graphs H. Like if you just sum over all such H's, this will never work. But like if we get this 2 to the dk factor, this is terrible. All right. So we need some other combinatorial property, and let me define this property or this object, and this is really central to our proof. So, and we call it cores. So we say that a vertex-induced subgraph F of a graph H is a core if any minimum vertex cover of F is also a vertex cover of H. Okay, so let me give an example. Let us look at this graph here. So a minimum vertex cover is contains maybe this vertex here, and then either this vertex or this vertex. Okay. So in particular, I'm claiming that the graph induced by this vertex set is a core. Okay. Because any minimum vertex cover of F, so what vertices does it have to include? It has to include this vertex, or this vertex, is also a vertex cover of the large. Another example, a bit simpler. Here we just know that the vertex cover, minimum vertex covers include this vertex here. So in particular, this is and this also shows that the core is always at least of size 3 times the vertex cover, like in courses. All right. So we have the following lemma, and we show that small cores always exist. So for any graph H, there is a core of size at most 3 times the vertex cover of F, with some additional property that, because we don't have time, I don't want to get into too much, but somehow what this is saying is that you can nicely characterize all graphs that are mapped to the same core. Okay, so you can somehow canonicalize the choice of your core in such a manner that you can nicely characterize all the graphs that be mapped to the same core. And this is very important, the structure, but I don't want to get into this. And now what I want to do, like if we go back to the previous slide, what I want to do is I want to replace the sum over these graphs H with the sum over these core graphs. There are much fewer such core graphs, and then hopefully this naive bound that we applied before will apply. All right, we go back to the edge axioms. This is what we had before. We can now rewrite this as a sum over F's, and then all the graphs that map to this core. And now you need to do some magic with this characterization of what is mapped to a specific core, but I think I'm slowly running out of time. So I think I want to leave it at this, and I just want to summary and recap. So what did we do? By duality, we got this notion of the delta pseudo measure, which gives us a lower bound on the coefficient size of the Sherali-Adams proof. We construct this pseudo measure using pseudo-calibration, where we somehow truncate this crazy sum here. And then we can actually argue that 1 is roughly mapped to 1. It's not so hard to prove that edge axioms are small, and then you get more involved to prove that any monomial is essentially compact. Right. So let me just say it again, what we proved. We proved that Sherali-Adams with polynomially bounded coefficients requires size n to the log n to refute the claim that a uniformly sampled graph contains a polysize field. This establishes Clique conjecture for Sherali-Adams with bounded coefficients. And some open problems. I want that someone proves the Clique conjecture for resolution. Please do this. And yeah, so a bit more concrete, the pseudo measure is very analytical, and I have very bad intuition to how it behaves. I would really like to have a combinatorial description of this measure. And I think if we get a combinatorial description of this measure, then we can make progress on the first problem. And somehow this is the issue why we cannot apply to resolution. And then finally, our Clique clique is only of size n to the 1 over 100, to be specific, n to 1 over 67. But yeah, can you improve this? I mean, this is ridiculous. It should be linear. Yeah, thanks.
Questions?
what about just getting like monomial size lower bounds, like removing the coefficient bound restriction? Is that possible or?
And so the main, I don't know, so the nice thing here is that we can go through LPs, and then by these LPs we can go through duality, and then duality gives us this nice object that we can construct. For the normal size measure, I don't know how to even do this. I just don't know how this measure. Yeah, it's just not as nice to behave, and I don't even know what it's. And yeah, I mean yes, it would obviously imply the resolution of
Yeah, sure.
So yeah, yes.
Well, I still have the same question about small Clique problem when K is a constant.
Yes.
So, for example, if K is a constant, what will be the size of the graph H, which you truncated?
It will be K. It will be constant size, right?
Yeah, K is constant. What will be your truncation bounds on?
Oh, thank you. Yeah, okay. It's some small constant times the maximum Clique size. Yeah.
Epsilon times K, yeah?
Yeah. So currently we had, yes, okay, thanks.
So I now want K to be a parameter, if you wish.
Yes, so before we had
Yeah.
E is equal to log n, and this is really capital B. So the expected maximum Clique size. Well, I mean 1/2.
Expected.
Yes.
Uh,
Our lower bound is of the form n to the omega of 3.
You mean Clique threshold, yeah?
Yes.
And it will be the same.
Yes, and you can really think of this as like as long as you're far away from P, then the common neighborhoods are well behaved.
And P is actually smaller than 1/2, so it can be. Okay, got it.
Yeah, this is
Got it,
this is
got it.
tiny, like 1/1000.
It's a bit unusual notation for given our previous paper, but I got it.
Sorry. I apologize.
So I think actually, before I ask my question, I think Sasha was asking if you could truncate at a smaller level if the lower bound you were hoping to prove was for like a smaller K. But I guess the answer is that you always somehow truncate it at something that is tiny constant times the max Clique in the graph you are looking at, right?
Yes.
No, not max Clique in the integral, but the threshold for a given P. What you expect.
Right. The expected max.
And well concentrated, yes.
Yes.
Right.
You know.
So my real question is, so what did you really use about the Clique problem here? It seems like, so in particular, like why won't the same technology work and give you some kind of, size with some coefficient bounded lower bounds for, let's say SAT or problems like that? And it seems like maybe the difference is that you have this completely spread out pseudo measure possible in this case, while in that case, it won't be possible. Is that what the difference is?
So a very technical answer to this is that we need to sum over these core graphs F, and we have roughly 2 to the d squared of them. And if you want to prove, two to the say n lower bound, then you would need to be d like linear in n. So this will give you a 2 to the n squared factor.
I see. Okay. No, but I understand like why things will break naturally for the Clique. I'm asking, say you wanted to do the same stuff, but for 3SAT.
I don't think I thought about 3SAT. I thought about coloring. There, I don't see any major obstacles. Like I think there are a lot of technicalities left to be figured out.
I see.
And I never thought about KSAT.
Okay. Yeah, maybe I can ask you more often.
Yeah, I would have to think about this.
Any more questions? Okay, so then let's thank you.